Was Einstein wrong? In 1927, Einstein and Bohr engaged in a century-defining confrontation, centered on one deeply unsettling experiment, the double-slit experiment. Who was actually right in this debate? Today, we may finally have an answer. If Einstein was right, then all of quantum mechanics would need to be torn down and rebuilt. If Bohr was right, this century-long controversy may finally be over. This very year, scientists at MIT carried out a new version of the double-slit experiment. Not only did this experiment put a definitive end to the debate, it also paved the way for entirely new quantum technologies. To understand why this matters, we first need to understand what the double-slit experiment actually is. More than 200 years ago, Thomas Young performed a simple experiment. He let photons pass through two narrow slits. Logically, if light were made of particles, the screen behind the slits should show two bright bands. But to everyone's surprise, the photons produced a series of bright and dark fringes, just like ripples on the surface of a pond. This showed that light was not behaving like particles, but like a wave. Then something even stranger happened. When scientists installed detectors to observe the photons' paths, the light quietly switched back into particle mode. On the screen, the interference pattern vanished, leaving only two ordinary bright bands. After repeated testing, scientists reached a shocking conclusion. How light behaves depends on whether you observe it. It was as if the light somehow knew that you were watching. Later, several upgraded versions of this experiment appeared, each more bizarre than the last. Before every new version, people thought, this time, it can't possibly know we're observing it. And yet, without exception, light always seemed to find a way to know it was being measured. Even delayed choice experiments, and quantum erasure, approaches that bend over backward to avoid disturbance, didn't work. Light behaved as if it could foresee whether it would be observed, and chose its behavior in advance. These discoveries sent shockwaves through the scientific community, and ignited fierce debate. At the 1927 Solvay Conference, Einstein and Bohr confronted each other directly. Einstein proposed a brilliant idea, one that could force light to reveal both its wave and particle faces at once. He suggested mounting the two slits on springs, allowing them to move slightly. When a photon passed through, it would gently push the slit, like a bird brushing past a tree branch. Einstein believed that by measuring this tiny recoil, we could determine which path the photon took, while still seeing interference fringes on the screen. That way, we would observe the particle nature and the wave nature at the same time. Two birds with one stone. Bohr said this was impossible. He raised two objections. First, according to Heisenberg's uncertainty principle, slits that appear fixed on a macroscopic level are never truly motionless at the microscopic level. They always fluctuate slightly, making it impossible to precisely measure the photon's recoil. Second, the very act of measuring that recoil to track the photon's path would disturb the entire system. The interference pattern would inevitably disappear or weaken. According to quantum mechanics, some quantities simply cannot be measured precisely at the same time, such as position and momentum. If you want to observe the particle nature of light, you must sacrifice its wave-like interference. Bohr's position was crystal clear. You must choose one or the other. Whichever photon you measure, that photon will not display wave behavior. For decades, the debate remained deadlocked. No experiment could definitively settle the issue. Throughout the 20th century, scientists performed countless double-slit experiments, using photons, electrons, and even large molecules. All results favored Bohr's interpretation. Whenever you tried to determine which path the particle took, the interference fringes disappeared. Yet none of these experiments could prove Einstein was wrong, because with the tools available at the time, it was simply impossible to realize the precise conditions required by Einstein's thought experiment. Still, Einstein's idea was far too tempting to ignore, and so the challenge continued to attract scientists, until nearly a century later, when ultra-advanced quantum technology finally made it possible to test the idea directly. In 2025, a team at MIT finally created a near-perfect version of the double-slit experiment, designed specifically to answer this ultimate question. Nobel laureate Wolfgang Ketterle remarked with awe that Einstein and Bohr could never have imagined that we would one day perform such experiments, using individual atoms and single photons. So how did they do it? And what did they discover? The MIT researchers completely overturned the traditional approach. Instead of using slits cut into a metal plate, they used the smallest objects possible, atoms. They treated the space between two atoms as a microscopic double slit, and let photons interact with them. They arranged more than 10,000 atoms into a crystal-like structure called an optical lattice. Each lattice site held exactly one atom, separated from the others and free from interference. They chose two very different atomic species, lithium-7 and dysprosium-162. To ensure the results were not tied to any special material property, all atoms were cooled to near absolute zero, just a few microkelvin. At such extreme temperatures, the atoms barely move, and can be precisely controlled using quantum mechanics. To create the slits, the team used rows of laser beams as optical traps. You can think of these lasers as invisible springs that hold each atom firmly in place. By adjusting the laser intensity, they could control how tightly each atom was confined. Once everything was ready, it was time for the photons. The researchers used an ultra-weak light source, so weak that on average, only one photon interacted with the atoms at a time. Each photon had the same task as in the original experiment. It had to interact with two neighboring atoms in the lattice, just as it would with two slits. Ketterle explained, "What we've created is a completely new version of the double-slit experiment. These individual atoms are the smallest slits you can possibly make. Each photon could interact directly with one atom, or enter a quantum superposition, and interact with both atoms at the same time. By reducing the experiment to photons and atoms, the setup was stripped down to the pure essence of quantum physics, free of noise and external disturbances." This was the perfect real-world realization of Einstein's thought experiment. One crucial detail: the team ensured that each atom interacted with at most one photon. This allowed the photon to fully preserve its properties, while interacting between the two atoms. At the same time, they prepared thousands of identical atom pairs. This allowed scientists to repeat single photon emissions many times, accumulating a clear pattern on the detector. The strength of this approach is that it cleanly isolates particle behavior and experimental outcomes, fully controlled by the experimental conditions, without the errors introduced by large slits or bulky equipment. Then the results came in. The answer was clear. The degree of wave behavior depends on how tightly the atoms are confined. When the atoms were held firmly in place, effectively collecting no path information, the photons behaved like waves and produced interference. When the atoms were loosened, the photon impacts caused them to move, recording which path information, and as soon as that information existed, the interference vanished, and light behaved like a particle again. The scientists explained it this way: the more loosely an atom is confined, the more uncertain its position becomes. The more uncertain its position, the easier it is for a photon to push it, and leave behind path information. In simple terms, increasing the atom's positional uncertainty makes the photon behave more like a particle, because its path is easier to reveal. Conversely, binding the atoms more tightly reduces uncertainty, and makes the photon behave more like a wave, because no atom can reveal which path it took. The team even fine-tuned the confinement strength to find a remarkable balance point. At this point, about half the photons behaved like waves, and the other half like particles. In this balanced state, the visibility of the interference fringes dropped to exactly 50%, and the probability of obtaining which path information was also exactly 50%. This matched quantum theory perfectly. This precise level of control beautifully confirmed Bohr's long-held view: if you want to know which path a photon takes, you must sacrifice its interference. This is an unbreakable rule, dictated by the uncertainty principle. This result is more than a beautiful demonstration. It is a major milestone in quantum physics. First, it directly verifies the principle of complementarity and Heisenberg's uncertainty principle within the framework of wave-particle duality. By using single photons and pairs of atoms to create an ideal double-slit scenario, the experiment eliminated all loopholes and disturbances, making the results strikingly clear. It further confirms that nature behaves exactly as quantum theory predicts, even at the scale of individual particles and atoms. This long-awaited experiment finally draws a line under the famous debate between Einstein and Bohr, a century later proving that Bohr's interpretation was correct. Beyond settling a historical dispute, the experiment also showcases a powerful new tool for quantum research. Using ultracold atomic lattices as quantum slits is an entirely new technique. It gives scientists a new platform to explore quantum phenomena with unprecedented precision. Researchers can place atoms in different quantum states, or even put the atoms themselves into superposition, existing in two locations at once, and observe how this affects light scattering. In fact, the MIT team is already considering even more complex follow-up experiments. They may use atoms in superposition, or allow the wave packets of two atoms to overlap and interact, to search for new forms of interference and entanglement. Atoms within the lattice can even become entangled with their neighbors, opening the door to clear modeling and visualization of entanglement phenomena. Another important application is the quantum eraser. This setup allows scientists to control whether which path information is preserved or erased. making it ideal for such experiments. For example, the team can let photons scatter first, then adjust or measure the atomic states, to effectively erase path information, and cause interference to reappear. Such experiments will further reveal how information and measurement shape reality. Finally, there is a symbolic aspect. The year 2025 has been designated the International Year of Quantum Science and Technology, marking 100 years since the birth of quantum mechanics, resolving one of the earliest and most famous controversies in quantum theory. In this very year, is deeply meaningful. Still, does this experiment truly prove that Einstein was wrong? Could there be undiscovered loopholes, or new theories we have yet to grasp? If you have your own perspective, feel free to share it in the comments. That's all for this video. See you in the next one.